Hello all, welcome to part 14 of the Wireless LAN Mega Primer. In this video, we will look at web in depth. So as many of you know web has been broken for a long time, it can be easily cracked and all that. And I think YouTube probably has 100 million videos on web cracking. So we will get to that, but before we actually talk about web cracking, I wanted to give you some basic understanding about web. That is essential because Aircrack NG practically would do everything for you, and I would not want the script kiddie mentality to kind of set in where we just use tools. So, little bit of basics about web. This was the first encryption schema used with Wi-Fi networks, and unfortunately, it was flawed from the get-go. I mean, when IEEE had just proposed that this is what we should do in web, there were papers coming out talking about flaws which were already there. Web internally uses the RC4 algorithm, and RC4, some of you may be aware, is a symmetric key encryption algorithm. What this means is the transmitter and receiver have the identical web key, which the transmitter uses to encrypt and the receiver uses to decrypt. Now, I think web is available practically on all access points, and the first flaws in web started coming out as early as 2000. But still, I don't know, for whatever reason, access point manufacturers still continue to ship it with web capability, and this is typically used by home users and manufacturing companies. Now, if you're wondering why manufacturing companies, well, if you remember the last time you went to Walmart or any other place, they have these handheld scanners which can scan the barcode and do interesting things. Now, these scanners, at least the old generation ones, had very simple hardware which could only support web and not WPA and WPA2. And this is the reason still now web is continued to be used in many of these places. So let me put it in perspective of the wireless LAN packet. If you remember, we had this huge packet which we discussed, and web is typically concerned with the frame body. So actually, the entire data which needs to be sent, if we want to encrypt it with web, would get encrypted, and there would be three parts to it. The first is something called the initialization vector. We'll come to this in a moment. The second part is the actual data along with something called the ICV, which is an integrity check. And this actually uses the CRC32 algorithm. We'll come to all of this in a minute. And the data and the ICV are encrypted. The IV, or the initialization vector, is not encrypted. It is prepended with the data and ICV, and all these three together actually are put inside the frame body. Now let's come to the initialization vector and understand about it a little bit more in detail. The initialization vector header field consists of two parts. One is the actual initialization vector data, which is 3 bytes in length, and then you have 1 byte consisting of 6 bytes of padding and 2 bytes of 2 bits of key ID. 6 bits of padding and 2 bits of key ID. So what is this key ID? Now, interestingly, if you ever go to an access point to configure web, so I've created an AP with the SSID PON.me and enabled security mode as web. So if you scroll down, you would actually find options to enter 4 different web keys. Now the interesting thing is, any AP could be configured with any one of these 4 keys, and the index of the key, whether it is the first, second, third or fourth, starting from the kind of 0 index, is what is represented in the key ID. So 2 bits, as you can clearly imagine, can house 4 values: 0, 0, 0, 1, 1, 0 and 1, 1. And this corresponds to any one of those 4 keys which are there on the access point, right? So with this, let's kind of move ahead. Multiple keys as we discussed, and these 4 keys starting from the 0, 0, 0, 1, 1, 0 and 1, 1 is what the key ID actually means in the 2-bit field as part of the initialization vector header field. Now let's understand the WEP algorithm in more detail. It's a bit technical and a bit more mathematical. I would not say technical, but more mathematical. But bear with me here, we will not go through the hardcore mathematics. But at a very high level, we will try and understand how this entire process works. So let's start from the very basics. We talked about the IV header field, which was 3 bytes, the initialization vector, which is 24 bits. Now, as far as symmetric key encryption is concerned, many of you may have heard of this term called cryptographic salt. So what is that salt? Well, typically what you want is the output of the cryptographic algorithm to be as random as possible. And this is where there are actually a host of attacks available which try and figure out various aspects of the algorithm, plain text attacks and whatnot. Known plain text attack and whatnot. And this is where in cryptography we actually use some sort of a random seed along with the actual key at times. Now in this case, the IV is actually a random 24-bit value which the access point or the client chooses. And the IV is generated randomly on a per packet basis. So right now let's consider that we are sending packet 1, and what we do is the access point generates an IV of size 24 bits absolutely randomly, ideally. Then the access point will take the WEP key, which could be either 40 bits in size or 104 bits in size, and actually go ahead and prepend the IV to it. So if you notice, this together is actually going to be either 64-bit or 128-bit. And this is what we are talking about in the case of WEP, which is 64-bit encryption or 128-bit encryption. Right? And so the interesting part here is the actual secret key is only 40-bit or 104-bit. The rest 24 bits as far as WEP is concerned is a random value called the initialization vector, which is generated on a per packet basis, both by the client and the access point. Now this is taken, and together this could be 64 or 128 bit depending on the key choice which we take, and this goes as input into the RC4 algorithm. The RC4 algorithm actually consists of 2 parts. One is called the KSA and the other called PRGA. KSA is the key scheduling algorithm and PRGA is actually the pseudo-random generation algorithm. Now, we will not go into the details of what KSA, PRGA, etc. is in this video. For people who are interested, I have covered RC4, KSA, PRGA all in an in-depth fashion in these 3 videos, where the first and second actually talk about RC4 and how to apply it in a C program, in the sense the whole algorithm, how to program it in C, and the third video is actually to create an encryption decryption software based on RC4. So have a look at it if you're interested, but I mean, I would actually say go through it at least once. Even if you don't want to, well, this is the background we'll kind of take right now, which is this is a black box called the RC4 algorithm, and where we push in this 64-bit or 128-bit key. The output, after we kind of go ahead and seed the RC4 algorithm with this 64 or 128-bit value, is a random key stream. When I talk about a random key stream, the RC4 can actually generate a very long key stream which should ideally be random for a given pair of IV and WEP, and this key stream is what will be used in encryption, right? So this is step 1, is generation of the random key stream, actually the pseudo-random, if you want to be very correct, key stream using the WEP key and by using an initialization vector which is random. The second part is actually to create the integrity check value. Now, what do we mean by this? Well, let's assume we want to send some data to the client, right? We are talking about from the access points perspective. This data can be of variable size, as one can imagine. Now, on this data, we actually apply a CRC32 algorithm, which is a cyclic redundancy check. Now, you can Google and go to Wikipedia if you're interested on how this works. Very simple algorithm will actually take 32-bit sized values from this data and take each one of these and do a very simple calculation with 1's complement arithmetic, and the output would be a 32-bit ICV, right? So regardless of the size of the data, the output of the CRC 32-bit algorithm is actually an integrity check value of size 32. Ideally, given a piece of data, you would only find that the ICV would always have to match, right? Which means if you run the CRC32 algorithm on the same data over and over again, this ICV value would remain the same, and that is why we can use it as some sort of an integrity check. Now, what we do after we generate the ICV is we concatenate the data and ICV together into one big block. So we have two things with us right now. The first step was generation of the random key stream, which can be exceedingly long depending on the size of the data we want to encrypt with it. The second thing we did was actually to take the data, generate the CRC32 ICV, and then concatenate them both together. So now we have a long key stream and we have data and ICV of fixed length. So we take the exact same size of key stream. So as an example, if the data was 12 bytes, the ICV is always going to remain 4 bytes. So 12 plus 4 is 16 bytes. So we generate key stream of size 16 bytes. And then all we do is a mathematical XOR operation, bit versus bit. So we take the first bit of the random key stream, we take the first bit of the data, we do a XOR operation, and the output is actually stored into the ciphertext. So important point, the ciphertext is actually going to be corresponding to the XOR of the random key stream and the data along with the ICV, right? Now it doesn't end here. What we now do, if you remember, the access point generated this IV in a random manner. And if you think about it, the client only has the web key. The client does not know the IV which the access point had generated as part of the seed to the RC4 algorithm. So now what we do is we take the IV as well and prepend it to the ciphertext. And here, when we say IV, we mean the entire IV header field, which actually consists of the initialization vector, which is 3 bytes from here, and then we have the 1 byte, which consists of the 2 byte key ID and the 6 bit of padding, right? So hopefully this was clear. I'm kind of heaving, a huge sigh of relief because this is quite a mouthful to go through each of these steps. WPA is much more complicated, which we will also go through in a formal way in coming videos. So stay tuned. The next step now is very simple. But before that, let's summarize this with a block diagram, which is part of the standard. So many of these diagrams I've taken from the standard directly, so acknowledgement there. Now to summarize, we took the initialization vector, we took the web key, we concatenated both of them. That acted as a seed for the RC4 algorithm, which produced the key stream. Parallelly, we took the plain text data, we found out the CRC32 integrity check value, we concatenated both of them, and then we took this key stream, the plain text and the concatenated IV, we ran a XOR operation, bit versus bit, and this gave us the ciphertext. We also took the initial IV which we had randomly generated and we prepend it to the ciphertext. So to give you a perspective, we said in the frame body, this is how all of this looks like, the IV, the data and the ICV. Basically what we have done is, we have just gone ahead and taken the IV header field consisting of the 3-byte initialization vector and the 1 byte consisting of 6 bits of padding and 2 bits of the key ID. Then we actually have the ciphertext, which is nothing but a XOR operation of the key stream which we generated along with the data and the ICV value, which is a CRC 32 bit operation on the data, took all of that, concatenated it together and put it inside the frame body field, right? Now, before we move forward, let's try and look at a live example of how all of this looks like at a packet level. So let me bring up our hacker machine, and I already have generated an interface Mon0, etc. So I'll just skip that part. Let me quickly run Wireshark. So I've configured an access point called PwnMe, which is running web. Let me start sniffing on the Mon0 interface, and I'm able to see broadcast beacon frames from that, if you notice here. Let me quickly add a filter so that we can just drill down and only look at packets from the PwnMe access point. I do not want beacon frame packets at all. Right. So now, as always, our favorite victim machine, my iPhone. Actually, I have nothing against the iPhone. I love it. I love my Mac. The reason I use it is this is the most comfortable device I can really show you on camera. So I have nothing against the device. Windows, Mac, all of it behaves exactly the same way as this does. No vulnerability on this. It's just that I love it so much that I want to show it off in all demos. So free publicity for Apple. Maybe I should ask for a sponsorship. So I go into these settings, and what we are going to do right now is start the actual sniffing. And here's what we'll do. We'll switch on the Wi-Fi. And if you notice, it's now connected to PwnMe. Let me dim the lights on this a bit. Right? And now we are connected to PwnMe. So what we are really interested in is just the data packets. Let me kind of just stop this here, and let me scroll up very fast and just figure out where we have the data packets. Right, so here are the data packets. All we are interested in is these data packets. So let me quickly go on top just to show you how the interaction has kind of happened. Right, so we've gone through the probe request response phase, as it's very clear, then the authentication phase, then the association phase, and from there on we actually had data being sent out onto the network. So let's only look at the data packets. Right, I could as well leave the beacon frame part of the filter, but I'm just letting it remain. So right now what we can see are only the data packets. I've selected the first data packet, and let's try to correlate with what we've seen. So what we said is, well, after the typical QoS control if applicable field, we would have the actual frame body, and this is exactly what we are seeing. You have the QoS control field. Let's not worry about it right now. And just after that, we have the web parameters. Now, the web parameter field is nothing but the IV field consisting of the initialization vector, which is 3 bytes. And then you actually have the key index along with the 6 bits of padding, which in this case key index is 0, as we are just using the first key to encrypt everything. Now, after this, if you kind of remember, what we said was we basically would have the data, and then inside we would have the data and we would have the ICV, but all of that is encrypted as part of the web payload. So this is where, if you kind of notice, I could select the data part. So the key index ends at this byte boundary here, all zeros. So just actually select the web parameters. After that, I'm just checking the data part, right? And here is the entire data part of it, which is encrypted. And after that, we have the web ICV, which, if you remember, we actually put it inside the ciphertext, right? You have the data which is encrypted, and then after that you have the ICV which is also encrypted, and Wireshark displays this separately as the next 4 bytes because the position of the ICV in web is deterministic, right? It's going to be actually added or appended at the very end after we finish off the data. And after that you see another 4 bytes which we know is actually the FCS of the packet. So this we can go back to our reference here, which is the FCS for the packet. Right, awesome. And this thing would repeat for every web packet. Right, you have the web parameters, 4 bytes here. The first 3 bytes are of course the initialization vector value. The next byte consists of the padding and the key index. Then I would kind of draw your attention here. As I'm selecting, you would know where one header field's boundary ends and the other begins. Very important to know that. Then, even though Wireshark mentions the web ICV that is down below, after the key index, we actually have the encrypted data. After that, we have the web ICV, and then the remaining 4 bytes which are here is basically the FCS or the frame check sequence value, right? One of the other interesting things which I want to draw your attention to is if we go to frame control and if we look at the various flags, you will notice that the protected flag is actually enabled and it says data is protected. If you remember, I think in the 3rd video we had talked about the web head, the WLAN header, where we had mentioned that if there is any sort of encryption, this flag would also be set, right? So very simple way by which you can actually find out whether encryption is set or not. So this is about how a web packet gets encrypted and is sent over the network. Now let's go back here and look at the decryption aspect. Now I will not spend too much time on decryption. It's very straightforward once you understand the encryption part. In symmetric key cryptography, typically it is just the reverse calculation. Let's see how. So now the receiver, which was my iPhone, does it know the web key? Absolutely. But does it know the initialization vector which was used as the seed, as part of the seed? No. So what it does is, it takes the message which it received in the frame, and if you notice, directly from the packet we are able to figure out the value of the initialization vector. So the receiver will take this initialization vector, it will go ahead and use the web key which it already had and concatenate both of them as we saw previously, and then it will seed the RC4 PRNG algorithm. If you notice, this is exactly now proceeding in the same way which we did previously, right? We come back to the slide. Now the key stream is generated. Now for a XOR operation, what we just have to do is just apply the XOR once again with the ciphertext and the original key stream to get back the plain text data which we had sent. So once the key stream is generated, the receiver takes the ciphertext, runs it through the XOR operation, and now if you notice, the ciphertext consists of 2 things. One is the plain text data and the other is the ICV which has been appended in the end. So now what happens is, the receiver does 2 things. It takes the plain text and calculates an ICV for the plain text by itself, and then it also looks at the ICV which is there within the packet after decryption. It compares both of this, and if both the values match, it knows that the data integrity is absolutely okay and the packet data has not been tampered with in any way, right? So this is how basically the decapsulation or the decryption works for web. Now, how do we decrypt web packets? So if you know the key, well, how would you know the key? Either legitimate way, you own the access point, you fed the key, or you can crack it. Of course, for networks, you have permission for, or you could actually go ahead and, these are the two ways by which you could know the key. For decrypting web, you could use Wireshark, or you could use a tool called AirDecapNG to get the plain text packets. Let me show you how. So let me go back to the attacker machine. And if you notice, we have all of these encrypted packets here. So how do we decrypt this in Wireshark? Before we do that, one interesting little thing which Wireshark allows us to do, if you go to statistics, there is something called WLAN traffic, and currently it will give you a summary of all the packets it has actually seen. So if you notice, this says, well, the PON.me network is all available, and this is some statistics about this network which I've currently seen. So this is like a mini arrow dump, if you may, right? And it gives you a good idea about what is there in the air. Anyway, now coming back, how do you decrypt these packets if you know the web key? Go to Preferences, click on Protocols and expand, scroll down and find IEEE 802.11, and if you notice here, it actually says, well, enter the web key if you know it. So the web key for currently is ABCDEF, ABCD, right? And after that, you have to enable decryption in order to decrypt it. So once you enable decryption, you can just click on apply, and what you would find right now, you can click OK, is all the encrypted packets have been decrypted. Awesome. So now we see that, well, on this packet the web parameters, everything is applicable, but we are also able to look at what is there inside the packet, right? And we are able to decrypt all the packets. So we can actually see the iPhone is sending out the DHCP requests, and it gets tired. I guess it goes ahead and then sends a couple of ARP requests, ICMP, IGMP, and all of that. Anyway, what I wanted to really point out here is how we can decrypt packets using Wireshark if you know the web key, right? Now, the other technique is also something which we can do. Let's just go ahead and remove the decryption. So one of the interesting things which I wanted to point out is you can actually mention multiple keys here, and Wireshark will try all of these keys. Actually, I think they allow 64 keys. Yeah, 64 keys, right? So now no decryption. Let's kind of remove the decryption. Apply, click OK. The other way to decrypt all of these packets is first to save them. So let me actually say File, Save As, and what we'll say is what we are only interested in is the displayed packets to be saved, right? Because we have applied all the filters and everything. And let's say this is web encrypted, and let's just quickly save it. So if we go back here, I think this should be saved in the root directory. So we have web encrypted 11K file which is saved here. So we can actually use this little tool called AirDecapNG, with which we can decrypt a PCAP file depending on whether it's using web or WPA. So we know the web key. So let's write down the hex value of the web key, ABCDEF, ABCD, not a great key to set anyway, but to be honest, why should we use web at all? That I should even worry about what key I am using. Even if I create the most random key, in the next video you will notice it's just very trivial to crack it. Anyway, now I give it the encrypted PCAP file, and it says, well, 53 packets read, total web data packets were 43, and total decrypted packets are 43. Here we go. Here is the web decrypted packets. We can quickly launch Wireshark and give it an input so that it just opens this up. And if you notice, we have the decrypted packets. Awesome, right? So this is how once you crack the web key, you can actually decrypt all previous packets which you had captured, right? And that is so very worrisome, because an attacker can keep collecting data over a long period of time, and when he cracks the key, all historical data is now available to him, right? And one of the poster childs of web cracking gone malicious is actually the TJ Maxx incident, I guess, which happened a couple of years back, where millions of credit card numbers were siphoned out, and the base attack was actually cracking into the web network of one of the stores of TJ Maxx. So now let's come back here, and I guess that brings us to the end of part 14, which is web in depth. Now, I talked about a lot of theoretical aspects, but hope I was able to present them in an easy to understand way. In the next video, we will actually move on to the web cracking part, which I can tell you is very, very, very trivial compared to part 14, where we really had to understand a lot of inner workings. Right? So that's all. Hope you're enjoying. Please leave your comments behind. I really love reading them, and that motivates me again and again to kind of make more videos. Thank you. Enjoy the rest of your weekend.